Okay, hello. This is the beginning of the Calculus 2 review. I'm not going to go too far into the explanations for why everything works and kind of explaining the logic of that. I just want to provide a very comprehensive look at the topics that especially show up in a Calculus BC type exam book, because I am once again using the Princeton 2020 Calculus BC practice prep book for AP Calculus BC. So let's get started. I want to say, and this is still a problem. The lines that just keep drawing. I don't know. So antiderivative. I don't want to say it's the opposite of a derivative, because you might have you might take an integral, or sorry, you might take the antiderivative of something, and then you might get several different answers be correct, in the way that if you take the derivative again of these several different outputs of the antiderivative, you'll get back to the integrand. And so I don't want to say it's necessarily the opposite, but I want to say it undoes the derivative, right? So with that in mind, let's think, okay, very basically, we know the power rule of integration. Don't forget the dx. You raise it first, then you divide by the power, right? That's just becoming more familiar, but don't forget the plus c, because it is an indefinite integral, right? There's no bounds on this, no limits of integration. So it's less about this answer right here being some definite area under the curve. It's just some arbitrary family of functions that are all shifted up in the xy plane or shifted down by some constant. And you don't know what exactly the constant is unless you have an initial value problem where they say, okay, by the way, this is a definite integral. By the way, at f of 0 equals 3, right? And so this is assuming that they ask you to take this, right? And so the integral of lowercase f of x, notationally, you'd get this uppercase f of x. And so then you know that this thing you just integrated, right? At x equals 0, it'll have an output of 3. So if you input an x equals 0 here, this term will go to 0. The c must equal 3 for the whole thing to equal 3 at x equals 0. Right, so this would then be your problem. So, and then this then means that there's a specific curve, and this is actually the curve we care about, right? This is the curve we care about because we know the specific vertical shift. So that's how this all idea comes back. But initial value problems aren't the only way to figure out what the function is, right? We might actually have definite integrals, which are interesting in the way that, like, okay, so maybe the last problem, they said, okay, f of 0 equals 3, right? Oops, wow, that's not what I meant. Okay, f of 0 equals 3. This is x squared. This is an indefinite integral, no bounds. And we figured out that the definite integral, we figured out that capital F of x, the antiderivative of this integrand x squared, is this whole x cubed over 3 plus 3 thing, because we know the initial value, okay? So what if then they said, what is f of 2? Well, now that you know this in particular, then you can say, okay, we know the function. This is a very simple algebra problem. You get 8/3 plus 3 by plugging in the x equals 2, and then whatever, like 5 2/3. But But there's another way to do it that's not, I mean, and this can get complicated if you have a larger integral, and then this whole one step, two step to fill out the plus c, because remember the first step was to get the plus c and next was like to figure that out. 3-step process. This is a 3-step process that we could probably do some other way. And this is where definite integrals come into play. All right, so what if we then had this idea? And this is something you learn with FTC part 1. But we can it's okay. We can look at it now, right? Oops, that's not what I want. Because I assume everyone has done their coursework and they know what FTC1 is. But let's say that we know that we want to this value right here, right? And they have not even given us the integral, actually. Let's assume that. They have not even given us the integral. They just tell us, maybe this is applied to a velocity position problem. Okay, lowercase fx is x squared. Find capital F of 2, given this little thing right here, this right here, right? And also know that the integral of f of x dx, this is f capital of x. Okay, so this is what you know. And this is something it took a long time to write, but this is something almost immediate in your brain. You see the thing that you have an initial value, and then you know that you also have to compute another value on the antiderivative graph. So this is very quick. It should be a trigger for you when you see it. Well, you can use FTC2 to say, okay, well, I know that the integral from 0 to 2 of f of x dx gives me f of 2 minus f of 0, right? And then you can say, okay, since this one is very clearly x cubed over 3, and you don't have to put the plus c because it's a definite integral, so this is not a family of functions, this is change in area, you know? Sorry, well, yeah. This is area under the curve, this is net change, this kind of idea. And you have your bounds, and you equal to f of 2 minus f of 0. Say, okay, well, I know what f of 0 is. It's 3. So then all you do is you do this plus 3 on both sides, and bam, that's a shortcut to getting your answer. And we can check this works. 8/3 minus 0 is 8/3 plus 3, and that's exactly what we got on the last slide, right? So this is another way that those are the two ways that I propose students, I mean, I don't know, I just said students, I and my classmates do these types of problems. Anyway, so initial value problems, those are quite simple. Indefinite integrals, also quite simple. U sub comes up when you're trying to figure out these types of integrals that have bounds. Well, it's more than just the ones with bounds, right? Yeah, you can do it. I mean, I think it comes up with ones without bounds, right? Indefinite integrals, you see U sub, and that's just one less step for you to do, right? So like if I see this, what if I saw some really gross thing like this? Right? What if I saw something like this and I don't want to distribute like this and then do power rule, because that would be very messy, right? So then all you do is you say, okay, how can I integrate this? And what I notice with U sub and polynomial terms and whatnot is, okay, whatever I want my U to be should be within 1 x degree of what's outside of that u, that potential u, right? So, what's inside is x to the first power. What's outside is x to the second power. This will actually end up making us do some tricky u sub. So let's try 2 examples. Let's try one where the power here is 3, right? And then here you see that as soon as you decrease the exponent of the x cubed to do the u sub, say x cubed plus 1 is u, du equals 3x squared dx. Always make sure you're paying attention to changing the differentials and whatnot. And don't forget to change the bounds if you want to. And then that sounds bad, right? Because you always have to change the bounds, right? What I do oftentimes is I write this u of 2 and u of 0 here to remind me that this is like changing the bounds, but oftentimes I revert back to terms of x a lot of the time. And so then I can just, do my FGC part 1 with just a simple change of, well, without even changing the bounds, I just come back at the end from the u terms. So I always just write it like this. Don't ever forget to change these bounds at this very elementary level, though. Okay, and don't ever forget to maybe manipulate your integrand with multiplication of constants and whatnot. And as another reminder, don't introduce variables, right? That would, like, don't multiply by x. Don't put an x into the integrand and then divide by 1 over x on the outside. That doesn't work, right? You can't poof a variable. So, all right, and then you say, okay, 1/3 u of 2, u of 0, and this is just simply du on the outside, and then you say u to the 7th power, right? And then you say, okay, integrate it, because this is the point of u sub. You integrate first, and then you produce this thing that you want. And then you say, okay, now that the operator is done, let me switch back into terms of x, and then you just plug back in u equals x cubed plus 1, and you change, and your bounds go back to being just 2, just 0, and that's how you do u sub, as a reminder. Now, spicy u sub is actually what one of my teachers called it, where we had that example that I had just had up on the whiteboard, where it was like this, right? And once you do u sub, sure, that's great. Once you do u sub, right? Sure. I changed it because I was solving it in my head, and the point I want to make is a little bit different than this. Right? Okay, so u sub, but then you have an x left over, right? But having x's left over is okay, but not having enough x's for your u and your du, that's not okay, right? And my point is, if you don't have enough x's to change your differential, then you can't introduce any variables, and that's the problem. But if you have too many, you can just do some algebra, and you can turn your u's into a form of x, right? And I'll show you how. So having too many variables, it's not the problem, but having too little is the problem. And you can remember that by just remembering how to do this, right? Okay, I can't change the differential. I mean, I can do this, right? sure, you can do this, but you have an x left over, right? And then you're like, well, this is not going to work because I can't differentiate, I can't integrate with these two variables yet. So what do? You just change it using some substitution. So, you know, u equals x plus 1 is the thing that you know. So u minus 1 equals x is just a rearrangement of that. And then you plug this in, and it says, oh, u minus 1, u to the 7th du. And you might be asking, how does this help? Well, in this case, it's a poorly written question, so it really doesn't help. But my point is just to illustrate the fact that you might have to do spicy u substitution. And just remember how to do it. You just rewrite your x in terms of u. All right. And technically, that's what we actually have been doing. Rewriting x's in terms of u. I mean, sure, you've been doing that kind of stuff this entire time. If you work back through u sub in the traditional way, you actually have been doing rewriting things, and that's how you get to that, maybe that factor in front of the integrand, right? That's how that happens. You're actually rewriting it, but there's different ways to look at it. The definite integral. So remember right Riemann sum, left Riemann sum, midpoint Riemann sum, and trapezoid, right? So left, okay, let's draw a curve. Okay, left, right? And what do we know about left Riemann sum? Well, if the curve is concave up and you're using left Riemann sum, right? It's concave up, it's going to be under approximation because, you know, you're missing out on a lot of area. This is your error, right? But then on the other hand, and you don't have to memorize this in any way, just if you're asked to remember this kind of thing, just draw a curve that's concave up, this one right here, and then just start doing left, and you'll very clearly see that it is under approximation. Then write Riemann sum by that same logic. If it's concave up, right is an over approximation because the curve is steadily growing up. And so if you start from the right, you're going to be over approximating all of this region that is actually under that point from which you started, right? And so, okay, and so, you know, concave up, but then if you look at concave down, the opposite happens, and oops, it's, you know, very simple to rederive it. Then here, left, that's not a left Riemann. And then you see, okay, left is an over approximation for concave down, right? And it used to be under approximation for concave up. And then right Riemann sum is a little bit different. In this case, whoa, 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 whoa. I did not mean to do that. Yeah, and then here it is the under approximation, where it was the over approximation on the other side. So just keep drawing stuff back. Trapezoid, and so how you calculate that, you know, width times height, length times width, sorry. Length times width will give you the area of the rectangles. And so when you're, you know, when you're looking at this curve, you just say, okay, it's broken down into pieces. That is not a good drawing. So let's do this. So maybe it's a right Riemann sum. Right? And then you say, okay, what was the width of this? And remember that the widths don't have to be the same, right? There's no stipulation that all of the widths are the same. In a given question, if you have to be like, if you're the one dividing up the data points in like a chart or something, they'll tell you, you know, for subdivision, left Riemann sum or right Riemann sum or something like that. And then you will take it upon yourself to divide it correctly, which is hard in my experience. And then you use those maybe unique, but maybe they're all the same widths, right, times the height of it. And then you add those up. Now, trapezoidal is a little different, and these are a better approximation because why? Because they are the average of the left and the right, I believe. I think that's what we learned. Let's do this curve, right? Trapezoidal says, okay, I have some width, I have this height here, but I also have this height here, right? I have this width, I have this height, and I have this height here. And so it does this kind of thing. And here, what you're doing is it's odd. I always have to kind of like think about a sideways trapezoid in this case, and trying to like remind myself, what is the width, or what is the height, right? What is the height? And these are the bases. And it's weird because we think of bases to be flat on the ground like this, but actually in this trapezoid, the bases are going this way. So then you take each trapezoid, again, the height, remember, the height does not have to be that equally spaced. So maybe the factoring and the addition is more clean if they are, but you should be comfortable to say, okay, 1/2 times the base 1 plus the base 2 times the height, or in other words, divide by 2. And this part right here is exactly why you know that this is an average between the left and the right Riemann sum, because not only are you taking this left height, but you're taking this right height, right? And then if you look at this, actually, it's kind of cool. You're doing that. You're splitting across it. So this is why this is the average. This is the path that the trapezoid's edge takes, right? So, and you have half the area over here, half the area over here. Okay, so that's trapezoid approximation. And then you have midpoint, which is very similar. And again, and just by knowing these, and then it goes through here, and maybe it goes through here, or something like that. So again, here you see you have to find the midpoint here. And it's very difficult sometimes to do midpoint because you're expected to know what the value is in between these two ends, right? And you're not allowed to create data. What that means is, okay, if you had a table here, maybe say this is x equals 0, this is x equals 1, no, x equals 2, x equals 4, x equals 6, right? And this point is at x equals 1. You're not, and if you have a table of x values, you're not necessarily allowed to create data sets, data points, and say, okay, I assume, no, it's looking at this table and not looking at the curve, that the x equals 1 value is between the x equals 0 and x equals 2 value, right? Do the rectangle widths even have to be the same? No, right? So don't be afraid to make different widths for your Riemann sum rectangles. And then always make sure when you are dividing up the data table for your divisions to like touch onto the next one. So like this, the Riemann sum rectangle that encompasses the area from 0 to 2, well, that'll have an area, right? Maybe it's this. But then the next approximation has to start again at 4. So then you have to start at 4 and go to, what, 8, right? And so don't skip an interval when you're creating your data table, right? You don't be like, okay, 0 to 2 is 1, 4 to 6 is 1, etc., because then you're missing out on all this area from 2 to 4. Okay. So then we move forward and we look at, okay, what is the definition? What is the infinite sum definition of an integral, of a definite integral, right? So let's say we want the integral of 0 to 2 from x squared dx. What this is, well, let's actually go from 2 to 4 so you can see it more clearly. Well, when we're summing up just Riemann sums, rectangular Riemann sums in particular, we know that we have a width times a height for each rectangle. So let's build the width. What is the width of this rectangle? Well, we know that the width of each piece will be infinitesimal, right? It's going to be very, very, very small because you're making thinner and thinner pieces. And so then, you're manipulating width in the first place. So you need to be using this limit statement. It has something to do with this limit statement. So the number of things you're adding up increases all the way to infinity for the integral, and the width decreases very, very close and gets closer to 0. And what is this numerator part? Well, it's not arbitrary. It begins at, well, let's think about what happens when n equals 1. When we have one rectangle, you're spanning the width and approximating the width from 2 to 4. X equals 2 to x equals 4. And then over time, then 2 pieces is then 2 to 3 and 3 to 4. So then it's 1. So you get a sense that 2 is in the numerator. And how do we get that? Well, we get, and I'm just explaining this in a way that I would derive it in my mind if I'm taking the exam. Okay, so that's the width. And then the height. The height goes in here. The height is how the function operates, right? So no matter what the no matter what the functions is, like maybe this was x cubed, or maybe this is x to the fourth, or maybe this is sine of x, right? This thing out here wouldn't be changing because, you're still approximating by the widths. Now, what's in the parentheses will change, and that's how I remember that the height goes in there because, well, the height is just a function of the input, and it's just the output. That's what the height is, essentially, right? So, okay, you say this is squared because the input squared is x squared, and that gives you the height. Okay, and then you also know that this is starting at x equals 2 for the first rectangle, and then it goes to the next piece of the rectangle, and the next, and the next, and it goes and moves by a factor of 2 over n. And you see this again, right? This is based on how many n's there are. That's how many pieces there are to get to the 4, right? So you say, okay, 2 plus 2n comes from 2. I'm trying to get to 4 from 2 over n pieces. If n is very, very small, then, fewer pieces, right? And it's easier to go. Maybe n equals 1, right? You'd be going from 2 to 4 in a single jump, because it'd be 2 plus 2 over 1, 2 plus 2, right? And so that's where all those derivations come from. So this is what I would say is the way of writing the series notation for this integral. But then you have to remember, what about the I, right? Because there's a left and there's a right Riemann sum, and where you start to differentiate between these two, where you start on, like this side or this side is largely determined by the I, the placement of, or this I plus 1, right? So then I say, okay, the input also depends on where you start, on the left or right or, whatnot. So then you also have this I factor inside, well multiplied against this change. So this is like a delta x right here. It's like delta xi, depending on where you're starting, to the left or the right and whatnot. So that's another thing to keep in mind. So this is the final way to derive that. I wanted to keep that point till the end. Okay. Then you think, that's great, but how many times will we have to do that? Not much. I've seen that a couple, maybe once or twice on practice exams. So, we look forward and we think, okay, fundamental theory of calculus comes next in this book. Actually, I've been skipping a little bit around, but we already know FDC1, and it's a very good way to solve these variations of the IVP problems, initial value problems, IVP, initial value problems, not IVP, IV problems. So I'm not going to go over that, but the second fundamental theorem of calculus, FTC2, is another thing that you'll be using often, and it is this idea that, and this comes up a lot. Wow, it comes up a lot. And this idea that you undo the integral. Right. And what do we know? Well, when you see something that asks for the rate of the area, the rate of the change in, change in this variable, well, that's a little too broad. Well, let's say we're modeling the accumulation of snow on a snowy day, and you're asking for like the rate of the accumulation. You're thinking, okay, if a function like this is modeling over time how much is accumulating, the rate of the accumulation is simply the derivative of the integral. And I think it's an odd concept because those ideas can, if you say them simultaneously, there are these things that undo each other. And that's completely true. So it's like, it's this interesting idea that like the kind of like how quickly this thing is accumulating is literally the rate of accumulation. That's why it's such a circular idea. And when you see these in Fear response problems, you'll identify it, right? The derivative of some integral type of function is maybe f of x, right? And you're thinking, okay, if f of x is the derivative of the integral function, well, then this has some very important applications in like curve sketching. And maybe if this is the graph of f of x, you're asked like maybe where does capital f of x or maybe capital F of t have absolutely relative maxima, right? And you're asked this question, and then if you want to say, okay, where does it have relative maxima? In Cal 1, the immediate thing you did was take a derivative. And you see it again, you have to take a derivative, but the derivative of this integral valued function will give you f of x, right? And it is a strange concept that, okay, this is literally the first derivative graph of capital F of t. This is the first derivative graph, so you think, okay, wherever it's 0 and undefined, and maybe I should have drawn an undefined place here, but it's too late. Well, actually, this is maybe a vertically, maybe this is infinite or something, a vertical tangent, and you say, oh, okay, look, it's crossing. Maybe it's crossing the x-axis, and so this should have a relative maximum because it goes from negative to positive from left to right. So we know that there's an extrema there, and then, oh, look, it crosses again, right? And then it crosses again. So these are all places where you know, because it crossed the x-axis and the signs change on the derivative, that the original function has relative extrema, and you need to be very comfortable going back and forth from your first derivative and your 0th derivative, or just your original function, conceptually, which is something I said in the Cal 1 video, because it'll come up with a question about FTC2, and then you're going to have to try and remember. And the way I do this is I center my view of the question around the information given. And the information given is the first derivative. And I tell myself it's the first derivative graph. This is the first derivative graph. Don't overcomplicate it, right? And then you from there, then you start making extrapolations and answering the questions. FTC2 also says that, okay, what is the derivative of this? I can make this some arbitrary thing. Oops. Right? I mean, what is this? And then that you realize that, okay, we have to do some chain rule on the upper bound, because not only is this x squared and the derivative, so the letters should be a little bit different. So the variable may be t squared dt, and we use w variables because we want to illustrate notationally that the derivative with respect to x of this variable changing is different from this change in variable, because this itself is producing a function. And this is changing the area over time, and this is the rate. And so the x's are controlling the change in the area over time. Okay, so anyway, so you say, okay, when I drop it down, it's x squared, but that itself is not the derivative, right? There's also a chain rule attached because your bound is not just x, right? So then it becomes 2x. So the answer is 2x cubed for what is d over dx of that. And so this entire question is that. Okay. Oh, and don't forget. No, you're fine. Yeah. Yep. This is all good. Okay. So next topic is mean value theorem. But although I do want to make a point real quickly, I was about to draw bounds because I was almost unsure if I was missing something. And the reason you don't draw bounds and like you can be confident is of course, and that's why I was pausing for a second. Normal the example we just looked at was a function. The result of the FTC to that entire theorem, the result of that in that application was, that curve that we just looked at or whatever it looked like, and so a function, will be produced by some variable function looking thing, which is 2x cubed, and it's not something with bounds or anything, and you just completely get rid of the idea of bounds too, because you took a derivative of the integral. Don't want to have to worry about the integral anymore or the derivative, so there's no need for FTC1 to come in again with the bounds. Also, yes, so when you use FTC2, make sure you don't plug in a value of x. So if they ask you what is, so if t squared was lowercase f of t, I just drew lowercase f of t, right? And if it asks you what is f of, I don't know, 3, so you're not going to, what you're not going to do, and I mean, you could just evaluate this way, but I assume it's not going to be given to you in this manner. If it asks you for what f of 3 is and it gives you a function, right? Yes, this is more common. You'll ask you what is f of 3, but then it'll give you the graph of this. And this is f of t, and it says, okay, maybe it says, this is in x equals 3 is what's happening. And you have to realize that this x came from the idea of the FTC2 rule dropping down the x. Then you have to remember that this whole chain rule thing happened and whatnot. But my point is that when you're applying FTC2, you don't want to plug in the x first, because that's like, in Cal 1 where you're like, okay, I found the derivative first, what is dy dx evaluated at x equals 3? You're not going to plug in the 3 first and then they take the derivative of whatever was the result, because that would give you 0 every single time, right? Because if you plug in 3, you're getting this constant value, and then you're taking the derivative of a constant, you're getting 0. So the idea was always first take the derivative to get the derivative function and then plug in the x. And this is a very important thing that almost confused me a couple times in the class. So you first apply the derivative operator, and not in Cal 1, but like in here where you're unsure, you have a derivative and an integral, and you're like, okay, do I plug in the x first and then figure something out? No. First, apply the FTC2 and figure out what the derivative function is, and you'll find that the derivative function is just, 2x cubed, as we derived here. And then you can plug in the x. So the x equals 3 for that example problem I just wrote, right? 2 times 27, so 54. And so keep that ordering in mind. Mean value theorem for integrals is really, it's frequent. It's like, what's the average value of the function? Or what is the average value for, I don't know, the number of, it's like, and this will come up also in concordance with the FTC2 problems, and you'll get really confused if you get confused by the terminology of like, what is the rate? Is rate talking about the f of x, and then what is capital F of x? So try not to get confused by those things. And then, but like, what is the average value of the function is a very plain example in wording you can see of function. No, I'm not going to try and think of a word problem. It is 2 a.m. So what is the average value of the function? Well, I'd like to think that, how do I remember that this is what this is related to? I remember that the integral itself is almost like telling you what the height is, because if you have an arbitrarily like thin rectangle, the height of it times its infinitesimal width, the height of it is important, right? And that's really defining what the value of this what is the area of this really small rectangle is largely defined by the height. And as you add up infinitesimally small rectangles, these are not, it's not zero. I mean, even if it's small, the area of each rectangle is not zero, right? And they actually vary a lot, and it's actually very good at, it's an exact value. Using integrals, it's an exact value for the area. So the area under the curve is largely defined by how high that rectangle is, because if it didn't matter, you would get the same value of every single definite integral ever, right? It depends on the height. And so I remember, okay, then the height of the function is the value of the function, the outputted value. And then I remember, okay, then what is the average thing you get out of the integral, out of the rectangles? Okay, and then that is just bound, let's just say b minus a. Right, and so that is the average value. You're essentially taking this area under the curve, and you're just dividing it up into how many x's there are. Well, how wide the x is, and then what that'll give you is some point. Oh no, come on. Okay, some point. Maybe that's too wide. Right, where this occurs. And this is an important idea. This area in the pink is equal to the area in the purple under the curve. And you can think about it like there has to be some average. You have to be able to construct a rectangle. This kind of goes into some pure math thing in geometry. Being able to square a shape and like produce, draw a square that has the same area as whatever weird geometric thing you have. And does it exist even, right? And then, but rectangles are less strict than squares. They can come in any sorts of weird configurations, super thin ones, super oblong ones, even they can even come in square form, right? So I think, okay, argument is that if you have a shape, right, with some area in it, and if you have a flashlight and you stand really close to a wall with the flashlight, this area is definitely smaller, but as you back away, the area gets bigger and bigger and bigger until at one point, at some instantaneous moment, you have an area that is equal to the rectangle's area. And so and I think of that idea here with like you have these bounds, and then if you draw an infinitesimal number of rectangles trying to equal the area under the curve, you're eventually going to get one. Maybe you start up here and you're like, is this equal area to the area of the curve? And you're like, no. Well, is this one equal? No. Well, okay, is this area equal? No. And then eventually, there is an instantaneous moment here at this specific y value, the average value of the function, where that height, that average value times this width is going to give you that exact value of the function. I don't know why I went on that tangent. It's an interesting concept that I learned. I thought would be an interesting way to show mean value theorem. So that's mean value theorem. Yeah. Don't forget that you are getting the average value out of something like that. That's like what the application is. Accumulation of functions. If you're asked for some sort of change, you should be thinking definite integrals, right? And so accumulation functions are simply showing you how much have you accumulated over time, and that is simply an integral, right? At this moment, if this is the rate function, right? This moment, you've accumulated something. Sorry, I can show that better. Yeah, at this moment of x or t, maybe for time, right? All of the time times the height of the function will be giving you some concrete value. So maybe the units of this line, right? It's maybe inches of snow per minute, right? And so you're thinking, okay, at this width, you're having some minute is giving you 3 inches of snow. And some minute here is giving you 4 inches of snow, and then you add up those minutes, the time span of receiving the snow times the amount of snow you're getting, and if you make infinitely thin and infinitely many rectangles, well, then you'll get the exact number or the exact inches of the snow that you've received from the beginning to this x value. So that's why the integral idea comes back, right? Of course, the integral is involved, and so this is another definite integral from 0 to x naught, where x naught is constant. This is a constant value on the f of t dt function, where this is f of t. Units are important. Remember that if you're taking the integral, what you're doing is you're taking the rate times the time value, right? Or you're taking the lowercase f of t and multiplying it by the independent variables units, which is often time. So inches per minute is the rate, or that's the f of t's units, and you're multiplying by the width of the rectangle, and the width of the rectangle is minutes, and so you're getting inches. Or if it was inches squared per minute, you just do inches squared over here, because that wouldn't be tampered by this multiplication. So units actually do come up a lot. Be sure to write your units. Okay. Trig function integrals and / more important integrals. This one should be very obvious to you, right? There's also, and this is the primary one you're looking for u substitution. If you see something like this show up in u substitution, where the u's on the bottom, du's on the top, it's very easy. Just it's the natural log. And then you can undo the u here, right? And you can substitute the x terms back in. Although I do want to mention that there's an absolute value here, and the reason you can drop when you do drop the absolute value bars, it's because the u or the input is never negative, and you want to make sure you're not plugging in a negative to the natural log function, right? And so if you have like a natural log of x squared plus 1, this is the x squared plus 1 is never dropping below the 0. Right? It's never negative. So you can drop the absolute value bars, and you can just use the parentheses like I did here. Integral of tangent. Let's actually take a step back. Integral of those very common things we looked at. Didn't mean to skip over them, actually. Let's get a... Let's see if I can find here. Yeah. So this is like a bank for me to make sure I'm covering the runs that are important. Sine of x dx, right? You're getting the opposite, the thing that if you take the derivative of, you get the sine of x. It's a negative cosine of x, right? plus c. And then you say, okay, integral of cosine of x dx. And how do you get there? Sine of x dx plus c, right? Because derivative of sine of x gives you cosine. And the negatives here always trip me up, so I take it very slowly when I'm doing these integrals in case I mess up those. Secant x dx. This one is simply, oh, sorry. You can't do this one yet. This is the one we're getting to soon. Secant x tan x is a derivative that we've seen before because it is the derivative of secant x. Let's see. Right. Okay. Integral of secant squared x. This is a common derivative because it is the derivative of, well, this is something we've seen before because it is the derivative of tan x dx. I'm sorry, tan x plus c. What about cosecant x dx? We don't know this one. Again, I made the mistake. But if it's negative cosecant x, cotan x, right, dx, you're going to be using cosecant x plus c, right? And if this were positive, this would be negative, right? Okay. And negative cosecant x, cosecant squared x is just that cotangent x plus c, but don't forget the negative because that's how it appears. But if this were positive, this would be negative, right? And you can do the whole derivative of this to check my logic. Okay, now we go back to where we were. And we think, okay, what are some more advanced integrals? Well, you can do natural log of x. You can do, what is integral of a to the x dx? This one is a to the x over the natural log of a to the x because, sorry, natural log of a plus c. Why do we know this? Because we know that the derivative of a to the x is a to the x times natural log of a. So if we want to take the derivative of this part, you produce that natural log of a term, kind of like waste material to the side, and this divided by natural log of a would be a constant. That would kind of eat up that waste, you know, so d over dx of a to the x over natural log of a. This is kind of a constant. You can pull it out. Natural log of a times what was the derivative of a to the x times natural log of a. Sorry. No, I was fine. Okay. So this was the constant, that term that got pulled out. 1 over, because it was division. Then you multiply. And then natural log of a terms eat each other up. And your derivative value was a to the x. And that's what you had, right? Okay. So that's another one. Then you have sine of x over cosine of x, in which we know to also be tan x dx. And the way I remember this is sine, again, from the Calculus 1 video, is just this, the negative Nancy, and it comes first. So it comes first in our antiderivative. Natural log, that's something you just have to remember. And then cosine of x is on the inside, and it's positive because it's, well, cosine of x. Okay, so that's the antiderivative of tan x, okay? Then you have, okay, what's the antiderivative of cotan x? And notice it's not cotan squared x, because then we already know that one, right? No, sorry, cosecant squared x, we know that one. And so, like, yeah, it's very easy to confuse those. And so this is something you just have to go slow, I guess, when you're thinking about your antiderivatives. Okay, what is this one? I remember, again, cosine of x over tan x is this thing. So the positive thing goes on the outside, then it's a natural log, then it's what's on the inside. Cool. Yeah. That's the antiderivative of that. And then we look at integral of cotan dx equal, oh, sorry, I just did that one. Then we look at integral of secant x, right? So this is nice. This is the 1 over cosine idea, right? And then this one is a little harder to remember, but if you remember that this looks like the secant squared idea, where like you have the tan x value associated with this, well, this is simply just secant x, the different integral entirely. And these types of integrals, you'll just have to remember, have this type of addition inside the natural log. But what do the functions look like that are being added? Well, those are just the associated things you normally think of with secant x. Secant x and the tangent x being added together, okay? Don't forget the plus c. Yep, good job, okay. Cosecant x is a little different, but same idea. And basically, here you have the negative natural log, because this was a positive up here, right? This is the, the negativeness of these associated terms. Always you see these signs have a problem, right? Like the derivative of cotan is, produces something negative. And then the derivative of cosecant, something negative gets produced. So keep that in mind, that the negative shows up here, but it's just the associated cosecant x plus cotan x that comes up, plus c. And the plus c is enough to come back. If you're doing a definite integral, of course, you just do the FTC one. Integral of e to the x. Do I even have to say it? E to the x, right? Okay. Then, although you notice that I have not done this one. Why? Because we need another tactic for it, which we learn, of course, in the next thing that I flipped over to, integration by parts. And the formula was the integral of u dv equals uv minus integral of v du. It's kind of an intuitive thing. I've seen the proof for it, and it's less as intuitive as I'll just say. I mean, okay. We're just going to think about it like, how do you remember the formula? Okay. I remember the integral of the first letter comes before the integral of the second letter in the alphabet, right? So, STUV, right, in the alphabet. So integral of u comes before the integral of v. And then the uv minus that part has to just, I think, come to u. Okay. And so how do I choose the u's and the v's? Well, I know based on the given integral. So this is going to be what's given to me, right? So this is kind of like the starting place. Based on the given integral, I have to choose a u and I have to choose a dv, right? The u, I know I will be differentiating afterwards, right? What I see in the problem, whatever I choose for the u, I'm going to have to differentiate it and produce a du eventually, right? So that's something to keep in mind. The u should be easy to differentiate, right? Easy differentiation. And the dv should be easy integration. And whatever you deem easy is, of course, relative, but the relative ease that you declare should be between the u's and the dv's and whatnot. So maybe the vu in this problem is super easy to differentiate and integrate, but the dv is hard to integrate. So maybe you'd want to just differentiate the v's. sorry, I'm using a letter, and that's not how that works because, you know, let's not use a letter because you will always have to integrate the dv's. So if you have something like this, because you have a function of 2, that's what integration of parts comes from, the multiplication of 2 functions together, right? It's not, there's no product rule in integration. There's kind of a chain rule thing, that's u sub. But this is as close as it gets. The thing that, you know, maybe the point I was making, maybe f is both easy to integrate and easy to differentiate, but g is just hard to integrate. So maybe I choose u to be g of x, because it's easy to differentiate, and f of x is easy either way, so maybe I choose it to be the dv. So the dv should be easy to integrate. Right, and depending on what you have, the relative ease between both of them, that'll just be deciding what you do. So here we see, okay, natural log of x, dx, where's the other function? The trick is the other function is just 1. So you're thinking, okay, which one is easy to integrate, differentiate? Both of them are actually easy to integrate. Well, okay, sorry. Both of them are actually easy to differentiate, right? Although we don't know what the integral of natural log of x is, hence the problem is integral of natural log of x. So let's not integrate that because we're deriving an equation from this, we're deriving a formula from this actually. So we don't even know what the integral of natural log of x is yet. So we have to use this as our u because it's easy to differentiate, not integrate. So maybe u is natural log of x. And the 1 is obviously easy to integrate. So 1 is equal to dv. And I usually write it. Where do I write it? I usually write it here. 1 is equal to dv. So then when we write our equation out, uv minus integral of v du, when I do all that, all I do is just, okay, what is the derivative of u? It's 1 over x. What is the integral of dv? It's just v. Okay. And so then I just multiply across like this. Okay, natural log of x. Why did I just put v? It's x. It's x. Integral of dv, because of the substitution, this is x. Okay. Okay. And then minus, yeah, so the idea is, you know, even if you're integrating the dv, you're getting dv to v. That's where the whole v idea comes in. That's why I wrote v on the left-hand side. But because everything is in terms of x, you're integrating the left-hand side as well, and you're getting the x out of it. So don't get confused by that little mistake. And then v, what was v? X. And then du was 1 over x. And dx, right? And so now this is just the same thing as x natural log of x minus 1 dx, because the x's cancel. Oops, that's gross. Okay. And then this is now x natural log of x minus x. And so this is, make sure you see the negative minus there. So make sure you're very comfortable with this formula. What's the integral of natural log of x dx? X natural log of x minus x. Yeah. Okay. That's a thing that it definitely wins the award for most easy to forget. Inverse trig, there are some formulas that you should remember the derivative of from the Cal 1 video. Look them up. What are the integrals of inverse trig functions? I don't want to write them all out, but the primary ones you should remember are like these. Like this is, what does this look like? If you see this in an integral, you should be very happy because this is something very familiar to you. This is the derivative of arctan. So if you integrate it, you'd get arctan. right? So that's great, okay? But sometimes it's not going to be so obvious, but something will look arctan-ish, right? It'll look kind of like arctan, but you can't necessarily just do this easy integration in one step. You have to make it look like arctan with some manipulation. So maybe you have something like 1 over 9 plus x squared dx in an integral, and then you say, okay, to get to, at the very least, what can I do? I could maybe divide everything by 9 to get the 1 to appear. But then if I do that, then the x squared would become x squared over 9, right? If I divide everything by 9. But that's okay, because if we get the 1 in there, and we have x squared equals something else, kind of like x squared, what we can then do is we can say, let me just u sub, right? So if the variable part kind of changes, we can just u sub, and that's completely fine, right? So okay. So then we multiply everything by 1 over 9. So we have 1 over 9 over 1 plus x squared over 9 dx, and that's the integral. And then we come up here, and then we say, okay, x squared over 9 should be, well, we got this part to look, we got the 1 plus part to look right, you know? And if we pull out the 1/9 because of the linearity property of an integral, right, it'll look almost arcanish. But then we just have to say u squared is what needs to be there, right? That's the goal. It should be 1 over 1 plus u squared, or variable squared. And so let's just do the u sub in this way. That gives us x squared over 9 is u squared. And then you say u equals x over 3. Yes, it is positive or negative, but it doesn't matter what you choose. It's something I found. If you choose the negative of it, and as long as if you remain consistent with your choice of negative x over 3, the derivative of whatever antiderivative you calculate will route you back to this original integrand. Okay, so then you use your u, and then you do u sub, and I don't want to work all that out, but those are the very important steps you should remember there. Also, come on. This should look familiar. Arc sign, right? Okay. So then you see lots of trig integrals. I don't want to, so I'm not going to review all of the very advanced ways to tackle integration. But remember that something that looks like this is not that bad, because you can rewrite an odd power of a trig function as 1 and then the even multiple of it. And the even multiples a lot of the times have these identities that we like. So remember that your trig identity for sine squared x is actually the same thing as 1 minus cosine of 2x, all of this over 2. This is something that you know, right? And this comes up often, actually. So that's your double angle, right? And the reason I remember it's a negative here is because not only in the sine squared double angle formula, but in the cosine squared double angle formula, you also have this same type of setup, except there's the sign difference. And so the cosine to the cosine conversion is positive because it's, it remains itself. It's kind of a positive thing. And these are completely non-mathematical ideas. but those are things that remind, help you remember. The sine goes to the cosine. Here it's a negative. It's like it doesn't remain itself, but the cosine remains itself. So it's just a negative here. That's how I remember that. And recall that this is the squared version. So you may have seen a square root involved with this formula. But that's because you were looking at sine of x equals, you know, the square root of all this. But this is sine squared, so you don't have to take the square root. So when you're replacing it, it's just a direct replacement to this formula right here. Okay. Also, remember your trig identities that involve with like Pythagorean identities, right? So like how to rederive this if you forget, right? You divide this side, and so that's the first one. That's the most obvious to other people, but these are, you know, less common to remember, but I have ways of remembering them. So this is how you derive it. You divide everything by sine squared. And then the other case is you, instead of sine squared, you divide everything by cosine squared of x. And I'm not going to rewrite everything. I'm just going to assume that you got my point. And I'm going to put the 1 over here, actually. No, actually. I'm going to keep it here. Cosine, cotangent of this plus 1 over that, secant squared. Right, so the way I remember this one's simple, sine cosine 1. Then this is 1 cotangent squared x equals cosecant squared x. It's 1 cottage cheese. 1 for the 1, cottage is cotan, cheese. This is something very silly that I've used for several years. What is cotangent 1 secant squared? It's how do I remember this one? Oh, I tan. So this is not cotan. Silly me. Yeah, that's why I wasn't remembering it. Okay. Don't judge me. This was definitely tan squared. Sorry. I tan for 1 second. Tan for 1 second. So tangent squared tan 1 second secant squared. So that's my way to remember these. And so a lot of the time you will get maybe an integral that's like, what is the integral of tan squared x? And you're like, I don't know, and I don't want to calculate that. Well, you can calculate it as the integral of secant squared minus 1. You just, rearrange. Okay. And also, if you're doing something like this and it's like, sine cubed, the integral of this, you know that sine squared of x is 1 minus cosine squared. So then you can just distribute the sign. You can rewrite this as sine x times sine squared of x. You can rewrite this as 1 minus cosine squared, and you can distribute the sine x. That sine x and the front, you can distribute that to the terms behind. And that's another trick. I'm just trying to remind you as many tricks as I can. Area between two curves. Remember that all this is if you have two curves, the area between them two curves is simply top minus bottom, right? And so you instead of and it's very intuitive. Why? I mean, you have your differential, you're adding up rectangles of area, but you don't want this excess area because it's actually being subtracted away from this. So the area of the top function minus the area of this bottom function is giving you this net area in between. So it's top minus bottom. And then the way you set the bounds is you figure out just where they intersect, because when they intersect, those are the, well, they might be given to you. The bounds may be given to you, but a lot of the time when you have to be careful when they intersect, because maybe then later on the bottom function will become the top function, and the top function will become the bottom function, and then it's no longer maybe f of x minus g of x, right? For this first little integral from this point to this point, it'll be f of x minus g of x, but from then on the top function is different, so then it must be g of x minus f of x for however long. So the only times it'll change are with intersections and whatnot, so just be careful with that. Or if like another function starts to exist or something weird like that. So those are where the limits come into play. And then horizontal slices, maybe, and the idea there is, okay, maybe you have something like, I don't know, like this. Like this is one function, and say this is another function. And a lot of times these won't actually be functions. And maybe you want the area between, and you're like, okay, cool. Like which one's top and bottom for this case? And then you might have to think like, this is the top for a while, and it gets like kind of hazy because you're like, okay, but then this one's like the top for another bit. So then you think right minus left. Why do you think right minus left? Because it's the same idea of like the more positive one on top. Right minus left for your integral of net, the net difference, right? Because when you were top, you had the more positive one minus the more negative one, or the less positive one, right? And that'll give you the net distance between. And the same idea happens here for right minus left. The one on the right is more positive. It'll be farther from this, from the y-axis, and so the differential for dy's, these are dy's, will be different. It'll be longer over here, and it'll be shorter over here. So then you do right, the longer one, minus left, the shorter one, to get this middle ground here. I also try and not get confused by the, the limits here, because the limits go from not bottom to top, but like, sorry. Normally they go from like left to right, like you start left to right for your limits, but here it is bottom to top. So that's an odd concept too, and I try also not to get confused by like reading a function of y, because you need to change all your functions of x into functions of y in order to use the dy integral and the differential and accumulate upwards, because you're using slices of width that are like this. And I mean, your widths are then again measured in delta y's. That's different from delta x. And the whole idea should then connect. I mean, it should be rather simple. There's nothing different about integrating in terms of dy. Your variable is just different, and you've done u sub to integrate in a different way. But again, something to keep in mind, that is possible, and that it is not any different, just a little different way of looking at things. And you should get the same answer if you do it right. If you model the same area in horizontal and vertical slices, just you would need different integrals and different bounds, and you need to rewrite your functions with f of x and f of y, depending on which way you're slicing. But if you do it right, you should get the same answer. And if you don't, maybe the integral isn't set up right. The volume of revolution, this is not crazy difficult if you draw a picture, right? So washers and disk method. So let's start with washer. Let's start with disk. Disk, okay. You're simply going from, you're taking this function, right? And you're revolving it around maybe the x-axis in this case. And it's going to generate this kind of cone, kind of like cone figure, right? Because this is going to start coming to this shape is going to start coming towards you and tilting towards you. And then eventually it's going to do this, and it's going to tilt downwards. It's going to tilt over there, and it's going to turn around. So it's going to be this conical figure. And the way I think of this is, okay, there's some differential x, dx, and you're revolving it, right? And this differential of x, which is a two-dimensional thing, because it has width and height, its rectangle, is getting revolved around. The same differential of x, different differential of x, different rectangle revolved around. And so over time, you're seeing that each becomes a disk. So this differential of x produces this disk, and this differential of x produces this disk, and maybe this one produces another disk. And you're adding these disks up because each one's going to have an area. And what happens if you get a width of areas, you get volume. You go from 2 dimensions, this two-dimensional flat thing, you're adding up the widths of each, you're adding up the area of each thin two-dimensional thing, and you compress it, and you're actually getting a three-dimensional object that has some width spanning from the limits of integration. You start, and then it'll be more obvious if you do the example, or you work through the formula. I try not to remember these formulas too much. I try to remember the cylindrical formulas, but so how do you do this? You're just calculating areas from left to right, and then these are just thin two-dimensional areas, and you push them together and you get the volume, right? So each one, then you have to think of the integral as calculating each thin area at a time, because it's in terms of dx, right? For each dx, you're doing some operation. Okay, so you start from the left. Maybe this is at 0, and maybe you stop at b. From 0 to b of the pi gets pulled out, f of x squared. And where does this come from? Well, each circle, each two-dimensional dx getting spun around, creating a circle. Every single one of those is going to have an area of a circle, of course, which is pi r squared is the area. And the radius of the circle is simply how far from the x-axis it is. So the dx is height. That is the same thing as the radius of the thing that's getting spun around. And that is the same thing as, well, what point on the function, what output of the function has its height, right? Because if you're spinning around this part of the function, this dx, it's taller than this dx, it's taller than this dx, it's longer, right? It's producing this wider circle. Right? How do we know that? What's different about them? Well, they lie on different points on the curve, and the different points of the curve have different function outputs. The radius is simply the function output, so f of x. And then you square it. So that's a disk. But if you have a washer method, it's simply saying that you revolved something like this. It's like a bigger function, but then you've also revolved a smaller function. What is the volume in between these two shapes? So how have you done this? This is simply this area minus this area gives you this area. It is not, however, the same thing as taking the big radius minus the radius and then squaring pi r squaring it. That is not true, because then you would get maybe, let's show you. Center, this is r, capital R. This is center, this is the same capital R. Center, little r for the radius. Center, little r for the radius. R minus r might get you somewhere like here. This might be r minus r. And if you take an area of a circle with this radius, that looks at nothing like what we want, right? That's just going to give you a circle that revolves around this point and is not relevant whatsoever. So it's r minus r is not something we're looking for. It's the circle area of capital R with a circle, area of a circle with radius capital R minus the area of a circle with little r radius. And so how we see this is then pi r of x squared minus little r of x squared dx. And so the big R is simply the big function that's top. Little function is little r. Don't forget that your axis of rotation doesn't have to just be the x-axis, which is also known as y equals 0. It doesn't have to be this. Although it is very easy to do it like that. You can also have you can be rotating around a horizontal axis that's not the y-axis, sorry, the x-axis. So maybe this is your function, but you're asked to rotate around the y equals -1 line. Well, then when you're writing your thing, your dx's, always think about stuff in terms of dx. Your larger dx, right, is not just the function output. Remember this? It is, well, let me write it like this. Right. It is this minus -1 to try and get you that extra length, right? So always, it used to be, with just the x-axis, it was r of x minus 0 in the parentheses squared, because you were just going from, yours going from here to here, right? But now you're subtracting from a lower area, so a lower line. So don't forget to account for that. So how would this whole thing look? That's a good question. So this is how I would write the second part. Oops, not a plus sign here. So this is then the integral pi r squared. So the pi comes up front. So this is then an integral that would give you the washer method, right? But at a disjointed place. But you can also revolve around a vertical axis. Same idea. Same idea. Just put your stuff in dy's and rotate around the y-axis. But what's difficult about that is really just putting it in the f of y function, and then kind of guess like people aren't familiar with thinking about it like that way. And then if you have a washer, well, let's just not give you that part. If this is a washer problem, having to think like, okay, this is the radius, this is the big R, this is the little r, and setting up your integral that way. So that would likely be a challenge, but that's why we have the cylinder method, shell method, right? So then you think, okay, what is the problem with this method right here? What is this? The revolving around the y-axis, right? it's the fact that we have to make differentials that are horizontal. So can we make a 3D shape with differentials that are vertical, but still rotating around this thing? And that's sure, right? Instead of having to rotate with the stick with the differential going this way and rotating around, you know, a disc and this way, and then, you know, this differential having to rotate around this way, instead of having to work with differentials like that, what if we cut this shape in a different direction? What if we take dx's again, because we like dx's, right? And we rotate them around this way. So then the rotation would be around this way. And you'd actually be producing something like a cylinder, right? Because you would be having this height that travels across and creates a surface of a cylinder, rather than this stick that's traveling around and producing a surface that's a circle, right? So this is a circle, and this is cylinder. So that's why shell method comes in handy, because we are now using differentials that are handy to us when we're rotating around the vertical axis. Then how do we get the surface? And so it's the same idea. What volume is simply this collection of areas, the thin areas compressed together. So you have, you know, you used to have these discs? Discs, that's the word. You used to have these discs that are 2D, and you have several areas of circles, and then if you add up all the areas of the circles from going left to right, you actually have this volume, since, you know, now the circles, when you push them together and you have a bunch of circles, you have some width, and then it's three-dimensional. Well, this is the same idea. You have a lot of cylinders that are stacked inside of each other. So they're stacked inside of each other, around and around. And so what you're compressing this time and adding up, they're surface areas of cylinders, right? So these areas, same idea, areas compressing together, and you add areas upon areas, and you have a volume. So you now have a width, but now you have a width of this cylinder, gives you the third dimension, and its volume. So what is a surface area of a cylinder? Because each differential and every single little cylinder is going to be produced by a surface area equation instead of just an area equation. Surface area of a cylinder, 2 pi r h. And why do we remember that? Well, this is 2 pi r. This is the circumference of a circle. Then you multiply by the height to extend this area around. And you don't need the faces of the circle cylinder. You don't need the faces of the cylinder, because the surface area that's important to us, right, they're just the sides. These sides getting added up. This is the volume of the shape, right? Okay, so we just need the lateral surface area. So you need 2 pi RH. So now we have an R of X function and H of X function, right? What's the R of H in this case? Well, if each one produces its own cylinder, let's just take this one for example. If this one produces its own cylinder, well, the radius is simply the X value that it's at. So as you have larger and larger X values, you're getting farther and farther and producing bigger cylinders with, you know, wider cylinders with larger radiuses, right? Radii. The X value that you plug into the function itself, right? That is the radius. So R of X is just the X that you're at that given moment, because, you know, of course, greater R's, greater radius, greater cylinder radius, right? I It has farther to come around. It's another idea you can, oh, sorry, it has farther to come around. I'm going to draw it in a more accurate way because it's no longer spinning around with the end of the stick touching the y-axis. It is literally coming around this way. Okay, and the h of x, well, that is the height of the cylinder. And what dictates the height of the cylinder? Where it is on the f of x graph on the function output. So this is just the function output. And this one, again, you know, if you drew a cylinder from here, sorry, if you drew a cylinder, come on, ugh. You drew a cylinder from here, the height would then be the function output for that given curve, and then the radius of the cylinder would be the x that gets you that output. Okay, and those are the formulas, and your A and B. They start. Okay, this is kind of a important point to make. When you're doing these cylinder methods, make sure that the 2 pi is only accounting for, it's counting for an entire rotation around the x, but you're not counting area over here. So like, so this, the 3D volume, when you're like making the cylinder while you're coming around, you know, that's 2 pi. You're using 2 pi as a multiplier to rotate around 360 degrees. 2 pi, 360 degrees, isn't that crazy? But if you have something like this, you don't need to rotate around 360 degrees because you're already getting all of this area, and you only need to flip it around 180 degrees to get the full effect. And so normally I don't think you'll get those types of problems, and if you do, and it's like symmetrical, I would just set, I would just consider the area here using the 2 pi equation. But if you have the entire thing instead of 2 pi, it's just pi, and I don't know. I'm not familiar with those calculations though. So I just stick with the looking at the side and doing 2 pi multiplier around the thing. And so A is then where it starts, B is where it ends. You can do cylindrical shells going around the x, and I'm not going to cover those because those are, because why not just do washer method or something like that, or shell or disk method? You know, there's no reason to do shell there. Cross section problems. These are fun. I like these ones. You're taking some area blob and you're saying, okay, the cross sections of each blob produce some 3D shape, and these are slanted outward. These are coming up out of the screen is what I'm trying to show with this drawing, right? And so, you know, in the problem, they'll give you a shape for the cross section. So they don't have to be these types of rectangles, and they won't be rectangles because that won't give you enough information to solve the problem. They'll give you some integral. They'll give you a solid. That's what they'll say. To find the volume of a solid whose base is a function. And it's a function like, you know, of whatever function would give you this, right? And then you say, okay, well, it's the integral of the function, right? So let's do a more basic example. Well, let's just say it's a circle. This is the base circle. So it is x squared plus y squared equals like 4, right? So this is the circle, and it is the base of a shape where each cross section, every single cross section itself is a square, right? It's a square. Those are bad squares, but my point is they're a square. And what that tells you is if you find the area of each square, s squared, and then you say, okay, but the side squared changes. And when I say side, I'm saying like literally the height of the circle. That's the side, and you square it. You give an area, right? Well, then the side changes, so you need a as a function of like, I don't know, x, right? And that's like s squared as a function of x. So, and then, you rewrite this thing for every single slice. So then you have your integral idea. You have, okay, this slice has an area that is given by s squared. This slice has an area given by s squared. This slice has an area given by s squared. And so then your area is just an integral of every single one of these slices depending on your s of x equation, as long as it's squared. But this is the case where they tell you that the cross section comes out as squares. This will be different for maybe circles. Circles, you'll know what the area of a circle is. They'll give you a semicircle coming out. Actually, that's what this thing is. This is your base. This is your base on some shape. And this is a semicircle coming out of it, and this is a semicircle coming out of it, and this is a semicircle coming out of it. All you do, model it to where you have some function that tells you what the length of the side is. So in this case, it's 2y, right? This is made obvious by like, okay, this is a circle sitting on the origin. This is y. This is another y that's equal to the first y. So 2y will give you side. And then you have to come up with some way, given the function, to figure out what the base is, what the side length is, or whatever. But this is the methodology to doing it. All you do is you first find the geometrical area thing, and I'll get you the formulas now. Side squared, square root of 3 over 4. This is the area of an equilateral triangle. So again, what do? You model the areas of every single cross section, where each cross section again is the area of an equilateral triangle. So then you'll have a of x, your s of x function. This is squared for 3 or 4, and then you have to figure out, okay, what's the side? And a lot of time they're pretty easy to figure out what the side is. It'll often be just the function itself, maybe, or if this is the region you have, and this is like y equals x squared is the curve, well, you know that each height and each side, and thus each s, is just the output of the function. So, whatever x squared equals, or whatever the function equals at this x value, maybe x equals 3 here, will give you a height of 9, right? And then 9 is your side for this arbitrary equilateral triangle cross section. And then you plug in 9, and that's your area for this cross section. But if it's a function of x, so it depends on each point of the function you're on for what area you get. But then you add up every single area, similar to what we've been describing. You add up all the areas from left to right, and you have this volume given. So an integral of s of x squared, square root of 3 over 4 times that. This is a constant. You could have pulled it out, etc. So that's the way you get that one. semicircle, radius. So normally a circle is pi r squared, semicircle, this is the area. So that's how that goes. Remember that you, a lot of the time what you're going to be calculating, like that same quadratic thing, what this gave you, for each little cross section, the x squared value is going to give you a diameter, not an area. So that's what you need to look out for these. So maybe then you divide by 2. So x squared over 2 would then equal the radius. And then you can plug that in to the integral. Okay. Pi over 2 x squared over 2 squared dx. And that'll give you every single, that'll give you the volume of this three-dimensional shape with a base of y equals x squared, and cross sections that are semicircles. Good. Length of a curve. Okay. Length of a curve is, okay, given a curve, this comes back up in Cal 3, which is the video tomorrow. So don't even worry. But this is one of the last topics I covered in Cal 2, in a class. The length of this curve from A to B is the same thing as the integral from A to the B. These x equals A and x equals B of the square root of 1 plus dy over dx squared dx. Yeah. And what this means is this plus this length plus this length plus this length plus this length. You add them up, and each length is like some Pythagorean theorem, where it's like the square root of the change in x and change in y. But since you change in x squared, change in y squared, and this is where the idea comes from. But if you want to factor out the x for some reason, right? If you want to factor out the x at the differential level, you're going to need a differential at the end of your integral, right? And so if you factor this out, you'll get dx outside of the square root, which will end up actually being at the end of the integral, right? And then you have the square root of 1 plus, don't forget, you need to divide out the dy over dx part by the dx that you factored out, right? And so that's where that whole equation kind of comes from. Very messily and quickly and not rigorously showed you the background to the equation, but that's how you remember it, right? You just factored something out. Okay. And if you want the length, oh Lord, if you want the surface area of a 3D shape, that directly uses this. Okay, so how do we find this? Is the next application, of course, is the surface area for evolution, which, okay, let's take the same function that we just drew. Now let's consider what would happen if we rotated it around the x-axis. We no longer care. I don't know what I wrote there. But we no longer care about the volume of the shape, right? Whatever's on the inside of this. When you rotate this, right, given a differential that you rotate around, you should be able to be visualizing the shape coming around in three-dimensional, in a 3D way. right? But we no longer care about like what's inside, like on, you know, what's being rotated, all this kind of like stuff that's on the inside being rotated. You know, that will give you a volume. It's solid, kind of, this is my area, and I produce some volume by rotating it. Well, that's not what I want. I kind of want like the length around it, and the length being rotated. And it's this whole shell idea method coming back almost to me, where I want maybe for this sum from some short length, and we're not looking at the differential case yet, because it's easier to think about this first from the perspective of some short length. So this length right here would then be the length, that integral thing we had, the square root of 1 plus dy over dx squared. So this is the same thing as the derivative, right? But it's not an integral because we're not massing a bunch of these yet, right? We just have one little portion, and that's our length. And when we have, in that last case, we put an integral because we had a bunch of little segments to add up. But this is just one. And then when we rotate it around, it'll produce some cylinder that has, what does it have? It has a radius. That depends, you know, it's a curvy kind of cylinder, which isn't, it's a problem right now because we don't really have a formula for that. But let's note something, because when we make it a differential case, when we look at the very, very thin rotation of it, we won't have some curvy cylinder. We'll have a, you know, relatively straight cylinder. Okay, so what do we notice? The radius of this cylinder is the output of the function. So radius, whoa, you see that? Okay. Radius, oh my lord. Okay. What happened? Why is this such a big problem? Okay. I don't know. I really don't know what is happening. I'm freaking out. Okay, let's just say radius. I'm just gonna write with my mouse. So the radius is the value of the function. If a function f of x gave you this curve, well then f of x is gonna give you the radius, right? But at a different x input, we'd be at a different length, and then if we took this part and we rotate it around, we would be farther from the origin. So it's still this notion, and so the cylinder produced by like these 2 points would have a much larger radius because the function outputs are larger over there. Okay, so that's why this is the radius. It's the function output itself, also known as y, right? Because y equals f of x. And then the other thing we notice is the height of the cylinder, or like kind of like the length of the edge of the cylinder. Because when we have a cylinder like this, right, the height right here is also important, right? And that is simply equal to the length that we have, this length. Okay. Sorry, the last video cut off. So I want to clarify. So we just noted that we have a radius that equals the y of the function. We noticed that the length, yes, the length is like the height of the cylinder, right? It's like, sorry, it's like, yeah, it's like the height of the cylinder, kind of like the width in this case, and that'll give us like some notion of lateral surface area. And so we think back to like disk method when we had these representative rectangles and we multiplied by 2 pi times the height of this, or the r, and we got these fan type things that, like, you know, they rotate around in 3D space, and if you fill it in, it's literally a disk with some volume. Well, this idea is we take with the surface area, we're kind of doing the same thing. We're taking this curve, we sliced a bit out of it, this representative length now, right? And then we rotate it around this x-axis here. We rotate it around, right? And so then we now have some notion of surface area. It's no longer some 2 pi, sorry. It's not pi r squared and getting this like idea of a circle's area, like, you know, rotating around in that way. This is surface area. So it's a surface area of a cylinder, right? The lateral surface area of a cylinder. That's what's getting produced by just rotating it around. And so if you want the value of this cylinder, and then if you have another little segment that's not infinitesimal, but you know, it'll get there as we take a limit. And there's a proof that I'm not going to go over, but this is the surface area of the next one. And if we add these ones up, well, of course, you're going to get some notion of surface area. You're going to get the surface area, right? So you can write, okay, lateral surface area is again 2 pi RH, right? 2 pi are constant, they stay outside the limit, right? AB is, you know, A is where the length starts, B is where the other thing ends, okay? And again, I'm going through all the nitty gritty of these types of things because the formulas are kind of hard to remember, so why not derive it on the test? Okay, what's the R? R is the Y, right? And what's the H? H is the length. And so let me give you myself some more room to write this. The length is 1 plus f prime of x. Don't, you know, this dy over dx, that was just the derivative, squared dx. So the dx comes outside the parentheses because you're adding up a lot of these. And so like now it makes sense that if you let the x, the delta x, run towards, like, you know, get infinitesimally small, the delta x right here, the delta x, if you let it get smaller and smaller and represent smaller and smaller cylinders, I mean, this still holds. You're still looking at some surface area along some region. All right, that's what's important to you, right? And so then, of course, this notion holds, and so this is the formula that we want. Okay. I want to remind you apparently in the book, it comes right after this, partial fractions. 3 types of things happen. Okay. If you have like x plus 1, x plus 3, and then you have like, I don't know, x plus 5 on the top, and you want to integrate this, right? You rewrite it in a way. And so this equals a over x plus 1 plus b over x plus 3. And so what does this mean? You didn't simply like break your denominator. That's legal in math, right? Legal. Illegal. But what you did do is you created 2 fractions that when you then, you know, you kind of undid the whole changing the denominator and adding the fractions things. So now when you multiply here by x plus 3 and here plus x plus 1, when you multiply these, and of course you have to multiply by 1. So this happens in the denominator as well. When you do this to produce this denominator, you're going to end up with something that looks like this. You're gonna get this, right? And we already know what the bottom looks like. We don't care what the bottom looks like. So then you have this algebraic statement of x plus 3 times a plus b times x plus 1 equals x plus 5. That's what it equals, right? And then you say, okay, and you do some sort of algebra. You can do a systems of equations type thing. If you can't cancel things as well and well enough, but if you say, okay, x equals -3 for this case, for a given case, you plug in x equals -3 here. It's 2. So 2 equals, then x equals -3 over here, zeroes out the a, so you don't have to worry about another variable. Your a is now the variable. If you have a fixed x, x is no longer the variable, right? You have a given x. You don't care to try and figure that out. It's not unknown to you. But a is, and you got rid of one of the variables. So now it's good for you because b is the only variable left. You have a -2 in the parentheses. So then you can calculate b to be -1. And then you do the same thing for b, and you can calculate b that way. Sometimes you might not be able to cancel out stuff, and you might have two variables. What do we know about two variables? Simply do a systems of equations and set two random x values, and then you'll be fine. If you just set two random x values and write a systems of equations from the resulting a, b, and this term with the given fixed x that you plugged in, and then you solve for a and b. That's the next way to do it. And a and b are your unknown variables there. But another thing I want to remind you is when you're doing partial fractions, if you have a repeated root, a repeated factor in the denominator, you have to account for the fact that maybe this happened. Right. Let me go back. Yep. B and A. So maybe this happened. And what this means is that, sure, you could have had some B, which has the x plus 1 whole square in the denominator. You could have had this term, but then maybe B is not equal to the question mark entirely. And so then you had another A term, which you then multiplied x plus 1 to, and multiplied x plus 1 to, right? And then maybe this gave you the rest of the piece to where, okay, maybe ax plus 1, sorry, a times x plus 1 plus b, maybe this gives you the question mark. So this piece is necessary, right? Or maybe it's just 0 and maybe b does equal question mark, but you just still have to account for this likelihood of happening. And so this whole thing is the same thing as, of course, this side being multiplied by x plus 1 squared, and this left side of this right side of the equation being multiplied by this, and that'll produce this statement right here, where this cancels out and you have a question mark left over. Then the x plus 1 cancels with only one of these terms, right? Because this is what we started with. I just multiplied by the x plus 1 on top and bottom just now to show you what I meant could happen. But we were trying to partial fraction decompose into this, and then the b's cancel, but this is distributed to both terms. Okay, that could happen. Or you have an irreducible factor, which then would mean, and by the way, of course, the reason you're producing these things is then you can have some constant, and so pretend we did figure out what A was and we did figure out what B was, then we have something to rewrite this as, and this is a very easy integral to evaluate, right? Because it's going to be some variation of natural log here, And this might be a little bit more work because of the square in the bottom, but it might be pretty easy as well. So again, pretty easy. Yeah, you can do your u sub with this because the bottom has first degree, so you don't need to introduce an x. You can u sub that one. You can solve the entire integral that way. Irreducible terms are another third one you could see on partial fractions. And what this one says is like, okay, you have something, but there's another factor included. This could be, so since x squared plus 1 has no nice factoring, you have to do like, sum of squares and imaginary stuff to get it to factor out nicely or into any way possible. You have a over x squared plus 1, but it's more than just a, right? You have ax plus b, right? So when you have this is a quadratic denominator, right? It's a quadratic factor. So what the thing we just looked at, let me sure we saw x plus 1 whole square. This was a linear factor, right? Squared. This is a quadratic factor, right? We're looking at what's inside. So this is a quadratic factor, so it's going to have a linear numerator. And by this similar logic, you're going to get this, and then same type of process. This was probably a little bit more difficult to figure out what the a, b, and c are because there's 3 variables. But alas, systems of equations will come in handy, I'm sure. And remember that natural logs and arctans always, or almost always, are very frequent things to show up in the antiderivative. When you take the integral of the result of this, a lot of the time natural logs come up and a lot of the time arctans come up. Last thing, apparently, the book wants us to talk about differential equations. And so if you see some sort of derivative that is with respect to like a function or maybe some operators that are like working, like a derivative that does something like this, right? And it's asking you to find the function it was. Well, this is an odd integral to take, but if you have the power of differential equations, what you do is separate, then integrate. You get all of the same variable on the same side, right? So you put the y's over here and the x's over here. So then you multiply both sides by y, you multiply both sides by dx to get them on their own sides, integrate. Same type of integration skills, although remember that you do want only 1 plus c, or else it'll just cancel out. And then depending on the plus c is when you will have to work with the initial value. So, then it'll say, okay, maybe y of 0 equals 5. So for all y's, you plug in 5. And for all x's, you plug in 0. And you figure out that c is 25 over 2. And so then the particular solution has this nice solved c in it. And it's a function. It's not just, so this is not a nice example because you have y squared. Particular solutions are literal function curves out of the entire slope field, for example, of things that could happen, right? So keep that in mind. It's not, it should be this function. It should be a function that's a particular solution. Okay. Okay. So remember to separate and be able to use these individual value skills that we've learned to do differential equations. Remember that logistics stuff comes up a lot, right? So something like a differential equation will be like, okay, y prime is ky times 1 minus I just paused it to make sure that the equation I had was correct. Okay. So what this is saying is that we have some, so this is the differential equation for it. And why do we know derivative and the function in the same statement? That's weird. Okay. But also the fact that we think of COVID a lot now that it's happened. It's very easy to I know what a logistic function looks like, and you think, okay, this curve is going to be increasing over time. It's only going to be increasing and approaching the full capacity of people being infected. So the population size, the carrying capacity in this is what they call it. The carrying capacity M is like this limit. That's like this horizontal asymptote of infected people that you get closer and closer to it. And every time it gets even harder and harder to get every single person in the population infected, right? But it does, get closer and closer. And so this is what we think of. And the rate itself, we'll think about when the rate's the largest. The rate's largest both when there's a lot of people to infect and to be in who are susceptible to being infected. So those are two things, right? So over here you have a lot of people who can infect, sure, right? But not many people to infect because there's so many people who have been infected. Or maybe it's like the zombie apocalypse. But back over here, there's this nice little the nice little balance. When the rate is the largest, the tangent line is the greatest. When there's a lot of people to infect and there's a pretty sizable number of people who can infect. So this is why it makes sense that the greatest slope, the largest value of this happens over here. Okay. And when you find the and if you've studied in pre-calculus what a logistic functions equation is, well, it's whatever you get when you try and solve this differential equation for the y equals version of it. So you get something like y equals m, this value in the numerator, meaning you're going to have a lot of computations having the denominator. They're going to get closer and closer to getting to this m value, but never going to get there. All right. Okay, it's MKT. Sorry. MKT. Just have to make sure. Okay, so as time goes on, this gets really, really large. Well, really, really negative, right? And so this, if you think, okay, what happens as t goes to infinity? You have e to the negative large means 1 over e to the large, right? Times b is virtually 0, right? And so over time, you're going to just be having m over 1 plus 0. So all of these computations over time are just bringing closer to this m, the horizontal asymptote, but you never reach it because you never technically get to infinity, right? Something that's just far and just out of reach. And the important thing to note is that when is this y-intercept happening, right? When does this happen? Well, this happens when, well, think about it, when t equals 0, right? Like it's like an initial value, right? Because you won't like have negative zombies, right? So it's like the initial value, t equals 0, m over 1 plus b e to the 0, because the t cancels out all of those things. So then it's 1, so it's m over 1 plus b. And so this is the y, this is the y int. Whatever this value is, will give you the y-intercept or the initial value, right? And so this is just another thing to note. Carrying capacity, the y, and the k right here. All right, cool. Do we have slope fields? Yeah. So then Euler's method is next, very close to the end. And you think, okay, Euler's method, very simple idea. It's kind of like you're projecting what will happen. Honestly, let's just draw this. This is the end, right? You're using what you expect to happen from here on out, kind of like a tangent line. Let's assume this carries over to the next step, and what happens here carries over to the next step, right? And what happens here carries over to the next step. It's just a bunch of approximations, so maybe the curve actually does something crazy and goes up that way. But because you're assuming this goes over to the next step and that one then drives on the next step and the next step, because of that, this is what you get. And you're approximating based off of your previous computation. So if you make a mistake on one step, you're going to be way off, right? So the formula is, and I don't really try and remember the formula, just kind of trying to remember this idea here, which hopefully that's what this video is giving you, a refresher on how to think about these things. So this is the formula where h is like the width. It's like the delta x for each step. So delta x, this is delta x, which is like h, right? And this is another h, right? Okay. And you're estimating the y value at some n, where n is like the number of steps you take, right? Okay. So we think this value right here is simply this value plus the slope times the time it takes. So, and why it's important to have this time factor, is because if this is your y sub n plus 1, and this is your tangent line, you have to know how much time has elapsed between this y sub n minus 1 and the next, and the y sub n. Because if this is the y sub n, you'll be at a completely different value if this is the y sub n, or if this is the y sub n. So the delta h is like a multiplier that's taking your tangent line and giving you more value. As you give more time, you're getting more value out of this slope or out of this tangent line, right? So, so that's why it's important to have both of these terms. So if we decide, okay, if h is like 0.2, it's going to normally be a pretty small fractional decimal value. Then you're going to be able to multiply this slope by this small thing, and then it'll be like rise, maybe like rise times run. Yeah, it'll be like the width times the height, and that will add height, which will add up to here, right? And then you do the next, and then, you know, maybe your delta, maybe your y prime for the next step that you calculate here is like this. And then you need this delta h, this another step of 0.2. And then that'll put you over here. And then you approximate from here. Okay, what's the next y prime? Maybe the next y prime you calculate is like this. So you get another h width, and you get here. All right, and so you do this iterative process over and over again, and make sure you recalculate these slopes for each of the steps. Slope fields, really just use logic for slope fields. I don't know what else to say, like, because these are like dy over dx given like x and y, something like that, right? Or maybe if it was just x, you know that as if it's just x, you know that as y varies, nothing changes in the slope. So it'll be like the same slope all the way up and down, and that's a very good indicator. And it happens for every single thing. Every single one of these, every single one of these x's has its unique slope. Sorry, that's really ugly. But going up and down, it hardly changes, or it doesn't change at all. If it just varies with x, same idea with if it's just y, right? It'll only vary going up and down, but left and right will not vary. X and Y is a combination. Then you just have to use, if it's like a multiple choice question, just use logic to figure out, okay, what looks flat, what looks positive, what looks more positive, what looks negative, what looks more negative, and so on and so forth. Also remember that a slope field is there with like these lines given at discrete x and y inputs are simply like tangent lines, because it would be really ugly to see every single curve drawn. I mean, maybe it'd be nice to look at, but it'd be overwhelming to look at every single x drawn out. So you have a slope field, which means that just because we're not drawing the xy slope of, you know, here of like decimal values, doesn't mean it's not there, right? And by that same logic, the slope field of this one does not mean it is traveling to this one necessarily. It does not mean it's traveling to this one. A lot of times that's how it works. But if it's like not pointed in that direction, like for example, if it's like this, or let's do something less crazy, like this, like that, right? This is very obviously not pointing at anything right next to it, right? Like that's not, it's not. So it'd be very silly to think that this has to connect to this and this has to connect to this, all right? It's, you use this, each slope as kind of like a booster, and you're like, okay, I'm moving around this way, and maybe oh, this is carrying me to the next area, right? And you use it as like kind of like a blow of a gust of wind, really periodically telling you which way to move along, and you just kind of hand draw it. And you can verify solutions by just understanding that whatever is given here, like whatever function is given here, right? You can separate and integrate a lot of time from this step. But you also should know that you can verify particular solutions given like a slope field, right? This whole idea of like, this is the derivative graph, by the way, you know, like red alert, this is the derivative graph. So if you want to verify something like a particular solution on this slope field, you know, just separate, integrate, get the y, get a possible function of a y in terms of x, and then you can plug in x and figure out what slope you're at, or sorry, what curve you're at, etc. Does this exist? Oh, it makes sense that this curve that comes out of this differential equation is like maybe quadratic, and then you like realize, oh, this is a quadratic function, you know, all these kinds of things. Just remember how to do all that. And also remember that, oh, I forgot. Oh, horizontal asymptotes, you know, being able to like tell like a whole steady line of these likely means that one of the solutions hits a hits a horizontal asymptote, you know what I mean? Like that's what that means. Yeah. So that is slope fields. And that is all. Thank goodness. So yeah, that is all of Cal 2. And maybe I'll make the Cal 3 video very soon because it's like 2 days before my exam. It's 4 a.m. in the morning. So, yep. Thanks for watching.